Is it your first time? That's very fun. Nice. All I know is that there's some blanket we have to put on the table.
Yes, I learned about that.
Conditions.
Okay, I was going to ask you if you knew what's going on. Okay, so everybody, there is one committee member. We're probably going to wait a couple more minutes and then we just get it going. If you think that there's not a lot of people here, we have a lot of people online. So if you can kind of at home with a lot of people here.
That's fun. This is a nice crowd. Can y'all hear me?
Yes.
Okay.
Yeah, that'll work.
Thanks. There he is. Hi, Dimitar.
Okay, so we have all the committee members in here now, so I think that we are ready to start. We always give a little bit of an introduction. I'm going to be quite brief because I know Chani gets very nervous if I go on for too long, but just to say that I'm happy to be here for Chani's defense. As most of you know, Chani joined us 5 or 6 years ago, I think it's fair to say. But then when the pandemic hit, she went back home to Montana, and she has been in Montana for the past 2 years, and she just came back for her defense. So we haven't seen Chani in person for a while, but we all know, as we will see, that she has been working hard, and she has come up with like 3 really nice results, which I will not go into obviously because that's something that Chani will show you. But I think it puts together a really nice thesis about how to deal with activity in stars, to be able to see the planets that go around them. So with that said, Chani, we're happy to be here for this public portion of the dissertation. Welcome to the family as well. Chani's family is all sitting on that side. Everybody else is sitting on this side. Anyways, I hope that you guys can meet each other at the end. And for the family, just so you know, this is a public portion of it. This is a celebration. You're happy to ask, we are more than happy for people to ask questions in the end. And there will be at 2 p.m., there will be another portion of the defense, the second portion of it, that is a private defense just between Chani and the committee. So if you can hang about the whole day, we will have that one starting at 2, and that's it. So with that said, let's get it going, Chani.
All right. Thanks, Mercedes. So I just wanted to start out by doing a few acknowledgments. I did not write them in my talk because I found that way too stressful. There's a lot of people that I'd like to thank, and I'm not going to get them all, but I want to start with my family. Thank you guys all so much for being here. I can't believe what a trek it was for you guys to even get here right now in the current travel status, so I'm so happy you're here. And to my parents and my grandparents, thank you for laying the pavement that I traveled to get here. Mercedes, you have taught me more than I could ever say, and all I can say is thank you. Munaza, I think you're watching online. I wouldn't have made it without you. There's no way. Jasmine, you have been my rock these last few days as I've been losing it, so thank you so much for that. To all my siblings back home and to all the aunts and uncles and cousins, I love you guys all so much. Thanks for watching, whether it's now or later. And with that, I don't know, there's so much to my committee. Thank you guys so much for joining. Andrew is someone who I go way back with, so I'm really excited to have him here. And yeah. Okay, so today I'm going to talk to you guys about tackling magnetic active regions when it comes to trying to determine exoplanet masses from radial velocity detection. And this is something that I've really felt pretty strongly about since I started my PhD, so I was really excited to be able to turn it into a thesis. So just a little reminder for my family that's in the audience, exoplanets are planets that are orbiting stars other than our sun. So we're all pretty familiar with the planets in our solar system, but all of the stars out in the night sky, they host planets too. And so if we pick one of those and blow it up, because it is a star that is not the sun, that is what makes a planet around it an exoplanet. Most exoplanets have been discovered via transit detection. So transit detection, it detects exoplanets by this periodic dimming of the star's light as the exoplanet passes between the line of sight of the observer, us here on Earth, and the star. And this actually, it provides us with an estimate of radius, as you can see here for the planet. We do need a little bit of information about the star, and we can use this signal here and the change in brightness and then the continuum brightness to actually calculate the radius of the planet. And luckily, we have a lot of nice estimates of our star from Gaia, as many of you astronomers know. So transit surveys like Kepler K2 tests have been able to confirm 4,000 exoplanets. And this is a big deal because exoplanet transits are pretty rare. And so they've been able to do this by observing a ton of stars because, as we've learned for not good reasons recently, a small percentage of a big number is still a big number. So let's talk about the discovered population that have been detected with transit methods. There are a couple important observations that came out of this population. So what you're looking at here is the size of the planets on the x-axis versus what is essentially an occurrence rate on the y-axis, to keep it simple. And the first thing that we noticed is that there's this huge excess of exoplanets that fall with radii between that of Neptune and that of Earth. And this was really surprising because we don't have these in our solar system. And so based on our sample size of 1, we were pretty surprised to find this when we looked at a very big population of exoplanets. The second thing that we noticed when we looked at this distribution of radii is this gap that exists from about 1.5 to 2 radii. And there's also this third feature, the radius cliff, that happens just about, I think it's about 3 our Earth. And this is this really steep drop-off in occurrence, and we just don't see many planets out here. And so a lot of questions have come up about these different features. So first of all, what the heck are these things made out of that we don't have in our solar system? It turns out that it's actually quite degenerate, and they can have many potential compositions. The second is, what is the origin of this gap? Something has to be driving that, something physical. And so we really want to find out what that is. The second is what's going on, the third, is what's going on at this radius cliff. Why do we not find many planets out here, and why is it such a sudden drop-off? 3 main processes have been hypothesized to explain the radius gap. I'm not going to go too much into them because I could give whole talks on them themselves, but the first one is photoevaporation. That's this process by which a planet loses its envelope, its gaseous envelope, because the host star is just blasting it with radiation. We've got core-powered mass loss, which is the same thing, but instead the radiation is coming from the hot core inside the planet that is still hot, young in its lifetime when it has just formed and has a lot of excess heat left behind. And then water-rich formation is a little bit different. It's probably the most unique of these 3 in that it suggests instead that these planets are forming initially with a bunch of water in their composition, so ice is in their cores and liquid in their envelopes. And then in terms of the radius cliff, there's actually only one thing that's been proposed to explain this, and it has to do with the solubility of hydrogen in magma. So I believe it has something to do with like that hydrogen at certain pressures can get sucked into the magma of the planet, and something about that process, it really avoids that radius gap. So at the end of the day, we want to know which of these are actually driving factors. And it turns out that compositions of small exoplanets are what are going to be key to figuring this out. Small exoplanet atmospheres, we can't really figure out very well yet what they're made out of. You guys, did I lose my slides? Yeah. Okay, there we go. So we have to come up with other ways to kind of figure out what these might be made out of. The first kind of clue that we can get about what these might be made out of is the bulk density of this exoplanet. And this is a plot that shows how densities can kind of help us estimate what these compositions are. And so you all are looking at planet mass on the x-axis against planet radius on the y-axis. And this is actually a little bit of a spoiler alert, but these are 2 planets that I analyzed that I'll talk about later. But here's a good example of how having a mass and a radius measurement of this gives us a bulk density. And this blue line represents a constant bulk density that's going to be consistent with ices, for example. So we can't say for sure what this thing is made out of, but we can start to kind of make some guesses based on the bulk density. But, of course, bulk density requires measurements of both mass and radius. And of the 3,000 small exoplanets that have radii measured, only about 300 of those have mass estimates. So 10%, it's a small percentage. Most of those exoplanet masses are measured via radial velocity detection. Put a little schematic in here for the fam just so you can catch up. But basically, when a star and a planet are orbiting, the planet goes way around the star, but the star actually does this little like wobble. And as that star has a spectrum that has these features. Sorry. Y'all can give me a heads up if you want. You think it's me, Phil? Better? Okay. So these stars have stellar spectra that have these features in them. This is like a total oversimplification, but as that star moves away from us and we observe it from Earth, we're actually going to observe that, that light of that star to be Doppler redshifted. And then as it moves toward us, we're going to see the opposite effect. It's going to be Doppler blue shifted. And when this happens periodically over time, as these planet and star go around and around, we can actually use the Doppler equation to convert that then to radial velocities for the star. So essentially, we are measuring stars like crawling like babies way out in space. It's pretty impressive. So this signal, this RV signal, it's going to give us with an estimate of the planet mass. This K right here is the radial velocity semi-amplitude, and that is proportional to the mass of the planet. So with some other information about this orbit that I'm not going to get too heavy into because it's pretty mathy, we can actually pull out the mass of that planet. And K values for small exoplanets can range anywhere from like less than a meter per second, which are very, very difficult to measure, all the way up to a few meters per second. So, why we're all here. Activity in stars makes it really dang hard for us to measure exoplanet masses. And there's a couple of different types of activity in stars. The first one I'm showing here are stellar oscillations. So these are these kind of periodic red and blue shifts that we see on the star, and this is the result of fluctuations in the stellar interior. And in the sun, this is going to induce RV variations of a few meters per second. And the nice thing is that this evolves on pretty short time scales. And so Xavier de Musc et al. Actually came up with this great observing strategy where if we collect a long enough exposure time, this actually cancels out. So over time, the blues become the reds become the blues, and everything zeros. Granulation is another type of activity in the star, and this is a result of convection. So basically, convection is causing these nice hot granules to come up, and then in the dark lanes, that's where material is falling back down into the core of the star. And because there's way more bright parts than there are dark parts, or rising parts than there are falling parts, we see this as a net blue shift because that material is moving toward us. In the sun, this is going to create variations of a few meters per second again, and this evolves on time scales of hours. These can be mitigated with observing strategies, but what we're really finding more and more is that eventually we'll need to be able to model granulation as well. But for now, we don't need to worry about that because active regions are just way too much of a pain. So these active regions come in a couple different forms, but they're surface features on the star that result from magnetic activity. So we have spots, plage, and faculae, and they can come in dark, cool form or bright, hot form. These, I told you guys that, are going to give you a net redshift, and that's because the magnetic fields associated with these, we talked about the blue shift associated with convection, those granules that are coming up. So those magnetic activity associated with these different features actually blocks that convective blue shift. And so that's how we end up with a net redshift. And these are going to induce semi-periodic signals, so not quite periodic, they're changing slightly over time, and they're related to the stellar rotation period. and I will tell you why now. So if we consider a stellar surface, and we just think about a couple features, some spots hanging out there, if this thing was rotating and it just went around and around forever and this stayed the same, we would have a beautiful periodic signal and it'd be a lot easier to figure out what's going on. However, these spots are moving. They start out at the poles and they move towards latitude, or excuse me, down in latitude, and then they also are evolving in size. So they get larger and then they get smaller and go away again. And so this is why we get these semi-periodic signals, and these can be really hard to characterize. In the sun, this can induce RV variations of up to 10 meters per second, sometimes even more from what I've observed. So these are really tricky, especially when we're looking for planet signals that have 1 meter per second. So we have this modern day suite of these amazing high resolution spectrographs that have gotten us down to an instrumental precision of 0.3 meters per second, which is actually the radial velocity induced on the sun by the Earth orbiting it. Unfortunately, there's a couple of those spectrographs for anyone who's curious. Unfortunately, those AR signals are going to, first of all, prevent us from pushing very much farther than lower than 1 meter per second. It's really hard to find small signals in the presence of these much bigger signals. And then also, even for detectable signals, it's going to make it really hard for us to get an accurate mass measurement and a precise mass measurement. The accuracy is the part that really concerns me, because precision we can tell, but accuracy sometimes we don't realize we're measuring the wrong thing. Just to show you what a problem these are, so this is some simulated data for a planet actually that Mercedes analyzed and published, and this is what the simulated data looks like without stellar activity. It's pretty easy to see that curve in the green points. And here's what that same signal looks like when you put stellar activity in. So you can see that this is making signals very difficult to see, and we're going to have to be clever about the way that we deal with these in order to come up with solutions. So in this thesis, I'm going to summarize three studies that I have done that the goal of these is really to just tackle these magnetic active regions in mass measurements and see how can we be more sure that we're coming up with the right answer and we're not suffering from the effects that these ARs cause on our mass measurements. So my first paper came out in 2021. It's called Exoplanet Imitators, a test of stellar activity behavior in radial velocity signals. The main goal of this study was to, I thought I was debunking. I shouldn't say that. I was going in with a little bit of a bias, but there were some things that hadn't sat right with me about how we were measuring ARs in GLS periodograms and some of the assumptions that we were making about them. So for those of you that aren't aware, a GLS periodogram is just a way for us to look for periodic signals based on their power. And so in this case, we see this signal at about 13 days. And in this case, we would look at something like this and we might ask ourselves, is this an exoplanet or active region? Basically, is this coming from a planet where we can fit it and get a mass measurement, or is this some stuff in the star that's going to trip us up? So, a couple common assumptions about AR signals that people go to kind of distinguish between the exoplanet peak and the AR peak. The first one is that active regions are going to induce peaks near the rotation period, or one of its harmonics being like over 2 over 3. And this was thought of because of those images that I showed you of the stellar surface rotating and thinking, okay, we're going to be somewhere near that. And the other assumption was that peaks induced by active regions, because they're evolving, if we, say, measure that peak and come back a season later, we wouldn't expect to see that still remaining. And so these assumptions, if they're wrong, could actually cause us to be falsely attributing active region signals to exoplanets. So let's say an active region signal doesn't occur at the rotation period and it lasts for a while. We would probably think that that was an exoplanet. So we've got a good example here of something that may be suffering from this. This is the Kepler-20 system, and it has 5 transiting exoplanets that we know are there because we've seen them in their transiting signal. But then it also has one additional non-transiting exoplanet that was confirmed by Bukave et al. In 2016, and that's at 35 days. The motivation for them fitting this planet in their data came from a periodogram. And first of all, there was this strong peak when they removed all of the known planet signals, left at 35 days. And they attributed this peak to an exoplanet rather than AR signals based on the two assumptions we talked about. So the first is that the signal was separated from its rotation period that was estimated by 7 days. So that can't be activity. And then it was also stable over 2 seasons. So these red and blue curves that you see are actually 2 different observing seasons. And we can see right here that we're still seeing a statistically significant peak in the blue and then a slightly less significant peak in the red. And so they took this to mean, okay, we've got a planet. But again, these assumptions were unconfirmed. So is it possible that Kepler-20g could actually be induced by active regions? This is what I wanted to test. So I came up with a method to investigate this in Kepler-20. I also applied this to K2131. I don't have enough time to talk about both of them, so I'm going to give the Kepler-20 example. And if you'd like to check that out, you can see the paper. So I begin by modeling Kepler-20 active regions. And I use timestamps from real observations so that we can make these as realistic as possible. And then I use these things called Gaussian processes regression. This is really mathy, so if you're not interested in GPs, all you need to know is that these 4 hyperparameters that help build the signal are related to things going on in the star. So the first one is the RV amplitude that is induced by in the star by the planet, by the activity. And then P-rot is the stellar rotation period. How fast is this thing coming back around? Tau is the evolution timescale of surface features. How fast are they growing and shrinking? And then omega is related to the distribution of surface features. So maybe we have a spot group on one side of the star and a spot group on the other side of the star. Or maybe we just have one. Here's an example of a modeled Kepler-20 active region signal. We can see a little bit of periodicity going on, but again, it's not going to be a perfectly periodic signal because these things change. Then I plot the GLS periodogram of the signal. I'm sorry, I didn't have a periodogram available for the real data, so you guys are just getting an example. But I think this says the point, where I plot these periodograms and then I'm recording the period of the strongest peak. Come on, there we go. So I'm going to repeat these first 3 steps for 100,000 iterations so that we can get a nice sample size to really get a feel for where these AR signals tend to peak in the periodogram. I then plot a histogram of those peaks to see the distribution and also calculate some occurrence rates at particular periods of interest. In this case, that would be the 35-day signal where the Bukave paper published a planet. So this is the histogram that came out of my analysis for Kepler-20. And what you're looking at here are different potential periods in the periodogram down here. And then, again, occurrence rates on the y-axis. And this is our period of interest, the 35 days. And these are all different harmonics and multiples of the rotation period, just to see if we do see an increased occurrence at those periods. So a couple notable things. We do see that most often that we are seeing max peaks occur at the rotation period of the star. However, AR signals were peaking at the period of interest, 35 days, almost as often. So at the rotation period, we see it peaking in 6.5% of cases, and at the period of interest, we see it peaking in 4.8% of cases. And that's within a 5% margin of the period that we're measuring. So this was interesting because all of this time we just have thought, of course, the rotation period is going to dominate the signal. We would have expected to see this huge peak here, maybe another really big one at P-rot over 2, and then not all of this little structure in between at these periods totally unrelated to any rotation period of the star. Aside from that, that second assumption that was made about activity signals never being able to remain stable over multiple seasons, we find that that is not true here. So in the cases where we did see a peak at the period of interest, 35 days, 17% of those cases, we actually saw that peak staying stable between multiple seasons. And so here's the 35-day signal, here's the full peak, season 1 and season 2. And again, that's within a 5% margin, so those do all fit within the 35-day range. So this was really interesting because that means that the signal that we attributed to Kepler-20g, maybe it's not from a planet, maybe it could be induced by ARs. And I don't know for sure. It really will probably take going back and analyzing that planet. I think some people have looked at it. But it is important for us to know that we can't make that assumption that this isn't the star. So that is a nice little summary of my first paper. My second paper pivoted a little bit more towards actual RV fits of exoplanets. And the main goal of this paper was to measure masses for 2 known exoplanets. So these transit, we know they're there, we know their periods. They're extra challenging, though, because the AR signals from both of the stars, for both K279 and K222, they overlap with the known periods of their planet, which is a pain, because when you're trying to pick out a, say, periodogram peak and you don't know how much belongs to the planet and how much belongs to the star, it's really hard to fit. I used a really important tool to address this challenge that are called spectral activity indicators. And these are features in the spectrum that have been shown to correlate with the AR-induced portion of the RVs. And a couple of these that some of you might be familiar with are like the spectral line full width half maximum, the contrast, and the bisector inverse slope. And I'll go a little bit more into bisector inverse slope, but I think for people who don't work in activity, maybe that's not super interesting. But so the strategy that I came up with is, okay, we've got the seasonal periodogram strategy, we've got activity indicators. Why aren't we looking at seasonal periodograms of activity indicators? And I actually did this, and my goal was to try to find a season where, even though in the full periodogram we were seeing this interference at the orbital period of the planet, maybe there's an individual season where we don't have that issue. So the data I used to investigate this are RV and activity indicator time series from HARPS North, and those are reduced with DRS 2.2.8. And they were both observed for 2 full seasons. So this is convenient because I can look at those seasonal periodograms and see if there's an ideal season to detect the planet. So here's an example of what these data sets look like when we have not only the RVs, but then several activity indicators as well. It's not important to know exactly what all of these are, but rather to just know that they do track active regions. In theory, we don't always see this to be the case, but they have been shown to at times. So here's an example of the periodogram that I created with the few activity indicators. I haven't included them all here because they didn't all have interesting things going on at the period of interest, but the ones that are important I've included here. So what you're looking at here is the period, it's up here, it's thrown me off, the period on the x-axis, and then the various RVs and activity indicators on the y-axis. And this is the period of interest for us, in this case, the known orbital period of planet B. And right here we're seeing in the dark purple the periodogram of the full RV set. In the cyan, the periodogram of the season 1 RVs, and in season 2, the periodogram of the season 2 RVs. And then the same for all of the activity indicators as well. There's no reason why we can't do this for those. And so some interesting things came out of this. So first of all, when we look at the signal at 11 days, the signal of interest, we see that peaks at PB is stronger in the RVs in season 1. And in season 1, we don't see any peaks in the activity indicators. So this is a pretty good indication that this 11-day peak right here is probably belonging to the planet and not the activity. Because in season 2, for example, we do see a peak also that is a little bit skewed from the 11-day period, which is a little bit suspicious in itself sometimes, but also we see these peaks in the activity indicators that could definitely be problematic. And so we don't know for this peak right here how much of that is the planet and how much of that is the star if we're seeing signals in these stellar activity indicators. But in this case, because we don't have any activity going on in the first season, there's a good chance that that's going to provide a more accurate exoplanet fit. I said that. Okay, so here's the other target, or the other star that we looked at. And you're looking at the exact same thing in terms of the seasonal periodograms. But this time we're interested in this 15-day period, the period of K2222b. And in this case, the season 1 RVs, again, are more likely to provide an accurate mass estimate, and it's for all the same reasons. So if we look in the RVs, we see a bigger peak in season 1 than in season 2. But if we look in the activity indicators, we don't see a peak in season 1 in the activity indicators. So that's a good indication, again, that this peak in the RVs in the blue is belonging to the exoplanet and not the star. So, also something that came out of this analysis is the potential existence of another planet around K2222. When we look at the periodogram, we know there's a planet here, but actually this peak over here is much larger. And that occurs at about 147 days. Sorry. And so the question is, could that potentially be another exoplanet companion? Okay, so the fitting strategy that I went in to deal with this situation where we've got one season that's better than the other is that I performed fits to the full data set, but then I also performed individual fits to just the season 1 RVs and just the season 2 RVs. And I'm hoping to confirm that the season 1 RVs agree, or the solution to them agree with the full set. Because if that's the case, then we know that that probably is truly an exoplanet if it agrees with the season 1 where we don't see activity. In the case of 222, I did a 1 planet and a 2 planet fit because we see that extra peak in the periodogram, and we want to know if that might be a planet. So in the case of K279b, the season 2 AR signal is not having a negative impact on the final measured mass. So it turns out that the orbital solutions between all of the RVs, the season 1 RVs and the season 2 RVs, all agreed within their errors. And so this is, for example, the semi-amplitude of the radial velocity signal, which is what's going to give you the mass of the planet. And so this is comforting because we suspected that season 1, or we saw that season 1 had minimal to no interference from activity. And so if the full fit is agreeing with that, it means that the full fit also probably is not suffering from that stellar activity signal at the period of the planet. Here are some final results or final plots for K279b. This is the radial velocity curve. And this radial velocity curve, the semi-amplitude, provides an estimate of the planet and the planet mass, which is 11.8 plus or minus 3.6 Mirth, which is the mass of Earth. And here's the transit signal, which had been fit before, but I actually refit them because we had some updated radii from Gaia. And out of this, we get a 4R Earth planet with a about 0.2 error. Okay, so again, in K2222b, we found the same thing. And that is that for the 1 planet solutions, they all agreed between their full season 1 and season 2 fits. So again, we're pretty confident then that we're not having that negative impact from the season 2 RVs. And the same thing for the 2 planet fits. This agrees with this, agrees with this. I adopt the 1 planet solution for now, just because if we look at the phase coverage of this planet, there are some serious gaps going on here. So it's hard to confidently call this an exoplanet when there's so much of the phase that we don't have filled in. So maybe later we'll have some follow-up observations and something can come out of that. But with a 147-day signal, it takes a long time for us to fill in that full period. That's a pretty long period. Okay, final results for K2222b. The RV curve gave us a mass of 8 Mirth, and the transit curve gave a radius of 2.35 Wirth. And so these are both going to have both densities based on those mass and radius estimates that are degenerate. They could have multiple compositions, and that's what we were talking about earlier with some of these planets between the size of Neptune and Earth. K279b, if it formed water-rich, which you may remember was one of the explanations for the radius gap, it's going to have a rocky and icy core, and then it's going to have an envelope of mostly hydrogen and helium with a little bit of water vapor potentially. And these are forward models that are done to kind of determine what these might be. And then if it formed water poor, then it's probably just a rocky core, no ice, and it's probably just hosting gas, no water vapor. K2222b, if that formed water rich, it's going to have a rocky icy core and a pure water envelope, which would be very interesting. And if it formed water poor, then again, we're going to have rocky core with a hydrogen helium envelope. Those tend to be pretty simple. Okay, so that kind of wraps up my second paper. Moving on to my third paper, which is the freshest. This is a new measure of spectral radio velocity and a new activity indicator that I have measured from spectra that I found are very well correlated in the solar data. So the first thing that you need to know before we get into this is that granulation causes these asymmetries in the shapes of spectral lines. And the reason that happens is that the shallow part of the line forms low in the atmosphere. And if you think about these rising granules, they're going to like burst out from the center of the star. So low in the atmosphere, they're going pretty quick still. But as we go to the higher part of the atmosphere where the deepest lines form, or the deepest parts of the lines form, we see that the granules by then have started to slow down before they start sinking back down. And so there we're going to see a much smaller blue shift than we see in the case of these farther down photons. Okay, and so this creates this asymmetry in the spectral line. And we call this the second signature of granulation because it is a result of those hot rising granules. And it turns out that that spectral line asymmetry is actually a really good activity indicator, not directly because of the granulation, but because of the fact that active regions suppress the effect of granulation. And so they're going to impact that line asymmetry, and really they're going to kind of straighten them out a little bit. And exoplanets, on the other hand, don't impact line asymmetry. So if we want to just measure the star, we're going to look for asymmetry because we can separate it from the exoplanet. An example of an activity indicator that's already doing this is the bisector inverse slope. So this isolates the AR-induced portion of the activity signal of the RV signal, by measuring this bisector, which is just the midpoint at all these different depths in the line, and then looking for this asymmetry. So if we blow that up, you can see that there actually is this change in shape. And that inverse slope is going to provide a measurement of that asymmetry that can try to track activity. Another thing that you need to know is that granulation also causes a strength dependence in the convective blue shift of lines. So what you're looking at here is a plot of strength, line strength or line depth on the x-axis, and then the radial velocity of all of the individual lines on the y-axis. So these are a bunch of different spectral lines. You see their wavelengths right here for one spectrum. And what we find is that weak lines, so these guys down here, they're going to form higher up in the atmosphere, again where, now I've got myself backwards, weak lines form lower in the atmosphere, where they're going to be more blue shifted because that's where the granulation material is moving very quickly. And then these stronger lines, they form really high up in the atmosphere. So again, they are forming where the granulation material is moving a lot slower. And so we're going to see way bigger blue shifts in the strong or in the weak lines than we see in the strong lines. And this is also a signature of granulation, but this one's called the third signature of granulation. And so the second signature of granulation, that line asymmetry, and quite related, and they both are a result of granulation in the star and that velocity gradient as the granules slow down as they rise in the star. Stronger spectral lines, therefore, are less responsive to AR signals because they're already less responsive to the granulation, and the AR signals are suppressing that. So this is something that hasn't been considered a lot in how we're measuring RVs and activity indicators or asymmetry from spectra. So the way that this is being done right now typically is that the known line strength dependence of these AR effects is not being accounted for. The second thing that's happening is that an average is being calculated across all of the spectral lines, but the lines, the deepest lines that we know are going to react least to activity are actually the ones that are being weighted the most. And this comes as a great example of when we may be trading precision for accuracy. Because if we want to track the activity signal, we should be picking lines that move with the most. And stronger lines give us more precise answers, but maybe they're not very accurate. So the question here is, are the current methods actually dampening these AR-induced signals by picking these stronger lines that are less responsive to AR effects? So we have this great solar data set that we can use to test these different theories. It's the Harps-North solar data set, and it's on the solar telescope, collected with the solar telescope, mounted on TNG. And this is super high cadence data, so there's a lot we can do with it. The DRS, again, is going to provide us with RV and activity indicator time series for that solar data. And when we remove the planet signals from the solar RVs, this is actually one of the most confident activity-only signals that we can get. Okay, so I actually have developed some new methods to track RV and the asymmetry associated with activity from a spectrum. So the first thing that I'm going to do is measure the RV and the skewness, which is a measure of asymmetry, for 765 lines. And these were published, I thought I put this in here, by Miklos et al. 2020, thank you. And the skewness is going to be a measure of line asymmetry around the core of the line. So you're just getting a couple of examples of positive, negative, and then a skewness of 0. So if we have a perfectly non-asymmetric line, then it should have a skewness of 0, and anything asymmetric, this should be a good way of tracking it. Then I'm going to plot the individual line RVs and skewness as a function of line depth to see, or line strength, to see that relationship. We already talked about this one. You already saw this one. We've got the shifts or radial velocities of the lines against line strength. That's called the third signature of granulation. And we've got what I have coined the fourth signature of granulation, which is when we look at asymmetries, we see the same strength dependence because, again, these are both related to granulation. So after plotting those, I'm going to correct for that strength dependence, which is something that hasn't been being done. And I do this by actually kind of stacking all of these plots on top of each other and then measuring a time averaged T-SOG or F-SOG, fourth signature of granulation. And so this is for just one spectrum, but you can imagine if we take a bunch of spectra from a bunch of times, we can kind of get that time average signal. So here's what they look like before removing the background granulation signal in the form of the third signature of convection or granulation and the fourth signature of granulation. And then here's after the removal. So we can see that in this case, like if we have these individual lines moving in response to activity, those changes are going to be a lot more obvious here where you don't have this big background signal dominating the shape of this distribution. So once I correct for that strength dependence, I'm actually going to, that's the point at which I now measure my new RV and new asymmetry-based activity indicator. And so this new spectral RV is set equal to the mean of this delta third signature of granulation. So what's left over after we remove that background granulation signal. And the new asymmetry-based activity indicator is the same thing, but just for skewness. Then, after that, I'm going to calculate some coefficients between these values, my RV and my activity indicator, because if we're going to try to use this activity indicator to track RVs, they better be correlated. And here's some values that we're tracking. So this is just one example of a plot. Right here we're looking at delta skew, which is my activity indicator, against RV delta T-SOG. And these values up here, the ones you need to know, are RS. That one's going to be the Spearman correlation coefficient. And so that describes how correlated these things are. So the closer this is to a line, the higher that number is. And we want that to be a high number. Then we've got the likelihood of a null result on that RS. So basically, this is a percentage telling us, or a likelihood telling us, that 0.92, how likely is it that that's just like a random signal and not actually based in anything physical. And then sigma res is the RMS scatter around this linear fit. So how much are these points dancing around this plot? And then we've got the fractional error on the linear slope. So we fit a line here. And in this case, it's a pretty good line. So we don't have a huge error there. But you'll see later that sometimes that can blow up. And it's a good indicator of if these correlations are legit or not. And then I actually have come up with another kind of measure of my own, which is called SNR-RV. And this is where 3 sigma RV is 3 times the standard deviation of RV delta T-SOG, and sigma res is this value up here. So this is essentially like the signal of the RVs divided by the noise left over after removing that correlation. Okay, so once I've done that for all of my activity indicators, I actually did the same thing for all of the HARPS North RVs and activity indicators, just to see, are we keeping up, are we doing better? Here is an example of the comparison for a combined solar activity levels. So what you're looking at here is the earliest times are the most active times. So we've got a high activity portion of the solar cycle, a medium activity portion of the solar cycle, and a low activity portion of the solar cycle. And what you may notice here is that, or an important thing to note, is that the RV that we're measuring, this RV delta T-SOG, is ranging way bigger RV ranges than what we're seeing in the RV DRS. And this supports that hypothesis that I had, that maybe the DRS method of weighting those less responsive lines is actually dampening that RV signal from the ARs. Now we can look at the same thing at max solar activity level, and when we narrow these down into these smaller time frames, it's kind of interesting because that's where we're going to start to see rotation signals, and these correlations really matter if we're going to use them in our RV fits. So the first thing you may notice is that we are getting a higher Spearman correlation coefficient than what's being obtained by the HARPS North DRS methods. We also have a slightly lower error on the slope, not a big deal. And then this SNRRV is quite a bit larger. And again, that's going to be a result of the fact that these are spanning a way larger range than these RVs. One thing to note, though, is that this sigma res is smaller in the case of the DRS values, which is the opposite of what we would expect, given that everything else, all the other metrics are better for ours. And so one of the things that I'm wondering is this low sigma res that's being returned for the HARPS North proxies, is that just because these aren't very spread out? Like if we just drew a horizontal line here and we measure the RMS from that, it'd still be pretty small because these things are like only spanning a couple meters per second. So now let's look at the mid-level solar activity. This is where that hypothesis really starts to get confirmed. So we're seeing that now we're doing much better on the Spearman correlation coefficient than the DRS RVs. And we can just see the difference, right? Like you can see that correlation. And this just looks a little messier. Another thing to look at is the error on the slope. Again, there's a huge error on the slope in the DRS RV, so that does not make me very confident in this linear fit. And again, their sigma res is way smaller then. And I think this just goes to show that it really doesn't matter what this fit is or how good it is. It's always going to give us a very low scatter, RMS scatter around it, because these just aren't very scattered at all, generally. So the low sigma res returned for these consistently, I think, are actually just due to that small range of the RVDRS values, which is a result of the dampening effect from favoring strong lines. So something to keep in mind is that a low, my little guy went away. A low sigma res value, so a low scatter around the linear fit, does not alone indicate a strong relationship between RV and activity indicators. It will maximize precision, but again, this might be where we're going to be trading off for accuracy, because if we try to disentangle these RVs with these activity indicators, we're going to end up with a signal that's nonsense. It might give us really good RV precision in the end, but it will be nonsense and we'll get an inaccurate result. Okay, so now, looked at that already. So now let's look at the minimum solar activity cycle. And this is where we really start to shine. So if you look at the Spearman correlation coefficient, you can just see that these are much more correlated. And that's compared with the RS of 0.16. Also, this is scary. We've got a 60% error on the slope of this line. So what that tells me is that like this line means nothing. Like this is not a real fit. On top of that, I already pointed out the Spearman correlation coefficients. So we still show moderate correlation here, and these could maybe still be used to come out with some sort of reasonable activity signal. But here, if you use these, again, this is going to just give you a nonsense signal that would then lead your exoplanet to have the wrong parameters as well. So, conclusions for this study. This new RV and activity indicator proxy that we've come up with are very promising. They're correlating very strong, showing better correlation than the DRS RVs. We have this essential next step, though, which is that we need to confirm that we're really tracking RV and the AR-induced portion through asymmetries in the way we think. So the way to do this is I want to add these injected exoplanet signals into the HARPS North solar data, and then see if using my method, my activity indicator and RVs, I can perform an RV fit that is able to disentangle the exoplanet and activity RVs. So this will really help to confirm if these are tracking what we think we're tracking. And if it's confirmed, then we really need to make attempts to improve that RV precision that was coming out. So that sigma res that was so small for all of the DRS values, we do need to get that smaller. That's important. But the most likely way to do that is using more spectral lines, because we're using 765 spectral lines, and the DRS uses 3,000. So that in itself also says something about the fact that we're doing better a lot of the time. So I just wanted to end off here by doing a few last summaries of the takeaways from these 3 different studies. Okay, so the first paper, some of the important things to come out of this are, first of all, most of the time we're not seeing periodograms peak at the rotation period of the star. And in the case of Kepler-20, this was 72% of the time we're not peaking within 5% of the rotation period, and 81% of the time for K2-131. These unexpected peaks also can survive multiple seasons, which we had only thought exoplanet peaks could do before. So we got to be careful. We could definitely mistake these for exoplanets. And the simulations that I use to test these things could really become a standard tool for checking the signals that we expect to see in our periodograms given a certain data set. Okay, moving to paper 2. So the first takeaway, I really think that comparing seasonal activity indicator periodograms and seasonal RV periodograms should become a normal thing. It really helps us to get a feel for what's going on from the season to season signals. And then it's particularly useful in cases like the planets I had, where you have the orbital period of the planet overlapping with the rotation period, or a rotation signal from the star. And when a season shows minimal interference, like we saw from season 1 in the case of both K279 and K2-121, we need to look at the fit to that season and make sure that the other fits that we're performing agree. And if they do, then we're a lot more confident. And then the last thing is just this potential second exoplanet candidate that's still out there around K2-222. I really hope that someone follows that up. It probably won't be me because I want to work on some other things more. But I think it's a cool planet, potential planet. And then moving on to my third paper. So the first thing, this new RV measure and new activity indicator are definitely promising. We have to do some more vetting before we can say for sure whether they're actually going to be what we need them to be to disentangle exoplanet and activity signals. Regardless, one thing that we can definitely say is that skewness is really good at measuring line asymmetries. It seems to be giving us exactly the expectations that we had for the relationship between asymmetry and depth of lines. And then the last thing is that we really need to consider the strength dependence of line shifts and shapes, because when we, as we've seen with the DRS, we might be suffering and actually dampening our AR signals by weighting those stronger lines. Oh, I guess that's it. Yeah, I'm sorry, I forgot my last slide. But I was just going to end with that. So, yeah.
it all put together. Good job. We have time for a couple questions. John.
So, in your first paper, you used Gaussian processes to inject signals into the data. And it was on the basis of these injected signals. Actually, how many did you do?
Oh gosh. Really have a full introduction. You want the histogram?
No, it was the one where you showed the.
Oh, the
there,
actual
right
that.
there. One more there. So you have these parameters, in particular the tau and omega. And so you have to make choices for what those are. And I imagine those choices are going to affect the conclusion that you draw. So I wonder how you were able to verify that your choices of tau and omega were realistic, since your conclusions were so dependent on them.
Sure. So the first thing, omega. So there's this really great work by Jeffers and Keller, I believe it's 2006, that actually went in and modeled a bunch of different potential kind of surface features on the stellar surface. And what they found is for a rotating stellar surface, no matter how complicated you make the distribution of surface features, put a bunch of spots, a bunch of plage, whatever it is, the actual signal is going to appear as if you're looking at one or two big spot groups. It's always going to average to that. And so that was really helpful because what it allowed us to do is place a constraint on omega of, omega has a value of 0.5 plus or minus 0.05. So that is how I constrained that, and I only showed one example, but I actually tried various omega values within that range. And they all gave pretty similar results. And then tau, there's a really great paper by Helen Giles, who came up with a relationship between the radial velocity amplitude from a star and the evolution time scale of the features. And I believe rotation period plays in that. So if you have some estimates for those, you're able to estimate tau, and that's what I did in that case. Thanks for the question.
Great job, Gretchen. So when you were discussing the correlations in the comparison study, I was wondering, do you know, because you were mentioning this already a little bit, like, do you know if these are like linear correlated, or are some people trying like other quadratic types of correlations?
That's a good question. So this is something that Steve and I actually went back and forth on a lot when we were working with this. Typically what's being done is linear. That being said, we have had discussions about whether that is a realistic expectation or not. I don't probably know enough of the details behind every single activity indicator to be able to say that, but I think actually it would be a very worthwhile to study to look more into that. But it's really hard because we don't know what we're looking for, right? Like, is what we're looking for a real signal, or is it just a garbled mess? So, yeah. Jeez.
So, the way I understood you approach paper 2 is like more of you just fit the RV. And then paper 3, it looks like you're trying to find some sort of indicator to like correct for activity. Is the next step, so paper 4 maybe, to like use what you're finding to actually do when you're fitting the RV, model out the activity?
Exactly.
Okay.
Yeah. So, and I want to do that with injected planet signals first, so that I know what the answer is. That's, I think, the best way to really test the method. But if that comes back looking good, then we can totally start to apply this to other stars. But again, I do think that there needs to be some modification with the method in which we what the best spectral lines to be using, how many. Perhaps we should be using different spectral lines to track activity than we're using for overall RV. Yeah.
So currently there's no RV correction that you're confident in? For activity RV correction that you're confident in?
Oh, actually, we use them all the time. To inform our Gaussian processes. What I am weary about is just like removing a signal, like removing this linear signal and then saying what's left over is your RVs, because My old advisor used to say you risk throwing the baby out with the bathwater. I thought that was kind of a funny expression. But basically, like, you might be losing some of your exoplanet signal by making this very general assumption that you can just remove that linear signal. But when you do decide to use an activity indicator, it's just really important to vet it in the periodograms, to vet it in the correlation plots, and make sure that you have good motivation for using it. Otherwise, you might be correlating with something that's nonsense as far as the activity is concerned.
Did you see another question? I thought you said another.
I said Cheems,
Oh,
and you said Chima. Yeah, so we were on the same page.
James.
Same person, different day.
Okay, I thought you James. Okay, so if we, I don't see any more hands. We do have time for one more question. But if not, thank you, Chani. This is very nice. And thank you.
And we all owe Mercedes a big thanks because this talk was not, like, was a lot more boring a few days ago. So she helped me get
Go Mercedes!